integrating functions of time. If I've got this velocity time graph and I want to find the change in displacement, well, the change in displacement will be the integral of this curve. Why? Because displacement is the integral of velocity. So that's what it's really saying. What's the integral from 0 to 4? Whereas, if it had said change in distance, then I'm going to have to break it up to when is it above, when is it below. So this is very similar to when we talked about integral versus area. It's the same idea. Displacement's just a straight integral, whereas distance is the area under the curve. And so now I've got to break it up when it's above, when is it below. A similar thing would happen if I'm looking at an acceleration time graph. The change in velocity would be the complete integral, whereas the change in speed would be the area under the curve. Which brings up derivative graphs. Might as well talk about this now. Because yes, velocity and acceleration and all those graphs, but really all we're talking about is derivative graphs. So if the function is displacement, then yes, we know the graph of the first derivative is the velocity graph and the graph of the second derivative is the acceleration graph. But on the original function, therefore, if we have a stationary point, then we must get an x-intercept, because that's when the derivative is equal to 0. If I had an inflection point, now what do we say about inflection points? Possible points of inflection happen when the second derivative was equal to 0. Now, that means the second derivative is an x-intercept, which means that the first derivative must have been a stationary point, because we're going through those levels. The stationary point, when we differentiated, got the x-intercept. If the curve is increasing, then I know the velocity graph is positive. If it's decreasing, it's negative. Well, what happens when the curve is concave up? If displacement is concave up, well, concave up was when the second derivative was positive. Therefore, velocity must be increasing, because how did we get to the positive? By differentiating the velocity curves. That pattern must still remain. So when it's concave down, the velocity graph must be decreasing and the acceleration graph must be negative. So that's how we can do it, by just visualizing it rather than actually doing calculus. Now, what about the type of graph? If the graph is a horizontal line, what happens when we integrate it? We will get an oblique line. So a horizontal line would just simply be y equals some constant. Differentiate a constant, you get a constant times x. So now the line's going to be at an angle. If I differentiate it, it's going to be the x-axis, because differentiate a constant, you get 0. If the original graph was oblique, then when I integrate it, I'll get a parabola. Integrate a linear function, you get a quadratic function. If I differentiate it, I must get a horizontal line. If the original graph was a parabola, then when I integrate it, I would have a cubic. And the cubic would inflect at the turning point, or the same x value. The oblique line when we differentiate it. Okay, again, things to remember. Integration, area. That idea. Integration is area, same idea. But if we're talking about velocity, distance is area, whereas the integral is displacement. If we're talking about acceleration, speed is area, whereas velocity is the total integral. Now let's look at some questions. Velocity time graph. It's a cosine graph this time. At what time during the period is the particle at rest? Okay, well, it's when v equals 0, isn't it? Velocity equals 0. That's what they're essentially asking me. I'm solving a very simple trig equation here. Cos t equals a half, yes, first and fourth quadrants. There's my acute angle. But I know it's going to be, well, they've restricted time to be between 0 and 2 pi. So we pi on 3, 5 pi on 3. And so I'll answer the question. What's the maximum velocity? Again, I'm not going to waste time. I know it's a trig function. I know my cosine function goes between -1 and 1, so therefore -4 cos t would go between -4 and 4. If I'm shifting everything up 2, it now goes between -2 and 6. So what's the maximum velocity? Well, it's 6. I just use my knowledge of the graph to solve the problem. Once again, sketch. Just a clever way to get you to draw a trig graph. Okay, amplitude is 4 units. Shift it up 2. Oh, but this time, flip it upside down. Period is 2 pi. I'll mark them off every pi on 2. There's my axes, but I'm going around 2 instead of the x-axis. A cosine curve it was this time, wasn't it? But we've shifted it up to cosine would start at the amplitude, but it's upside down, so it'll start down at -2, it'll go up to the axis and up and down. There's my graph. Calculate the total distance. Possibly that's why they got us to draw the graph, because distance, we've got to think about area above, area below. So I've got to split it from 0 to pi on 3 and then pi on 3 to pi. Okay, let's substitute in, and whoa, well, I didn't say it was going to be a nice neat number, but there it is. 4 root 3 plus 2 pi on 3 metres is the total distance travelled. Acceleration time graph they've given me this time. Okay, write down the time at which the velocity is a maximum. Now we don't have an actual function here, although because they're straight lines we could work out the equation of these lines if we wanted to, but that's not what we really need to do, because what this is saying, we know velocity will be the integral of acceleration. So therefore what it's really saying is, write down it's a maximum. When is that integral a maximum? Well, it's at t equals 2. How do I know that? Because I'm looking at the area. When is the area the most positive? Because I'm talking about velocity here. Most positive. And if you imagine travelling along the t-axis, the area is getting bigger, it's getting bigger, it's getting bigger, it's getting bigger, it's getting bigger. Then you hit 2, and all of a sudden it's a negative area, so the value is going to get smaller and smaller and smaller. So it must happen when it's t equals 2. Other way of thinking about it, velocity is a maximum when v to t equals 0. But anyway, however you do it, you get t equals 2 seconds. When is it furthest from the origin? This one's saying, well, when's displacement a maximum? When are you the furthest away from when you started? We know it's going to be a maximum when the derivative is equal to 0. But derivative is velocity, and velocity is the integral of acceleration. So with this graph, that's what I'm trying to find. When is this integral equal to 0? When is the area above equal to the area below? It was nice they gave us straight lines so we can work out the area of the rectangles and triangles. Looking at it, it's a lovely symmetric one. It's got to end up being at t equals 4. So that will be when it's furthest from the origin. Okay, this one they weren't nice straight lines. We've got curves and what have you. It's a velocity time graph this time. Velocity time graph. Use the trapezoidal rule. Yes, a clever way of making sure you're studying the trapezoidal rule. But estimate the distance. Well, we've got to use the trapezoidal rule because we don't know the equation of the curve. So we can only estimate it, and trapezoidal rule is what we could use to do that. We know the distance will approximately be, because it's going to be the area under the curve, hence why we're using the trapezoidal rule. H on 2, the end ones, 2 times the ones in the middle. There's not a lot in the middle because they've only given me 3 points to work with there, but there's my table of values. So 1 times the end one, 2 times the one in the middle, substitute it all in. Okay, 7 metres, approximately. 7 metres. You're now telling me it's initially at the origin. During which times is the displacement decreasing? Decreasing. That's when the first derivative, or velocity, is less than 0. Well, I can just look at my graph now and say, well, when is the velocity less than 0? And that was when t was greater than 5. That's when it started going that way. Estimate the time when it returns to the origin. So again, it's another one of these saying, well, when is the displacement equal to 0? But hang on, displacement in this case is the integral of velocity. So we're talking about the area under the curve. We want to know, when is that integral equal to 0? When is the area above equal to the area below? I'm going to need the picture for this, so there's the picture again. Looking at that, I'm going to look at pieces of it, because remember I'm trying to say when's the area above equal to the area below. Just look at those 2 triangles, at least that's nice and symmetric. I know they're going to cancel each other out. T equals 4, we estimated was going to be 7. We now want to know that rectangle on the right, when is that also equal to 7? So that's what I'm trying to find here. So when's that equal to 7? Simply solving it. Eventually we get, okay, it'll be about 1.4 further on, so 7.4 seconds. All right, let's now go and find our displacement. Well, at least a picture of it anyway. There's our original velocity time graph. So we're going up a level. So I'll just draw some axes directly underneath it. I just find that easier because then I can translate information down from the above one, and plotting in key points. So it looks like 2, 4, 6. I've put 8 in there as well. What do we know? We were told it was initially at the origin, so I can plot that particular point in. We estimated that it was at 7 when t equals 4. So I'll plot that point in. Remember the symmetry of the areas there. So I now know that at 6 it must also be at 4, because it'll return to the same spot. The area of that triangle is 2.5. Hence why I've marked in 9.5 on the y-axis. It must have gone to 9.5 and then back down again. It returns to 0 at 7.5. That's what we estimated in the previous question. So I've plotted 7.4 in. Now, this bit. I look at my velocity time graph and I notice v is steeper between 2 and 4 than it is between 1 and 2. Remember, steeper means it's going quicker. So therefore it must have covered more territory between 2 and 4 than it did between 0 and 2, because it was going faster. So I'll plot 2 certainly below 3.5, below halfway. I might have exaggerated a bit, but I put it well below what 3.5 would be. When t was greater than 6, I've got a constant, and we know that when we integrate a constant, we get a straight line. So there must be a straight line joining those 2 points there, and it keeps going. There's the rest of it. Now, how do I get the rest of it? Between B and D, I've got an oblique line, and we know that when we integrate an oblique line, we get a quadratic. So I just drew like a parabola between those points. And for the rest of it, I said, well, it's just going to be some sort of a curve. So I just did a curve to join up with it. And that gives me a picture for the displacement. I mean, it might not be 100% correct, but it's a reasonable representation of what it could be. Last example. I think it's the last one anyway. 2005 HSC, a velocity time graph this time, and again we're told it's initially at the origin. At what time is the displacement a maximum? So displacement's a maximum, we're saying when is the area the most positive it could be. Also I could say when is velocity equal to 0, because the first derivative would equal 0. However I choose to do it, that's going to be at t equals 2. At what time does it return to the origin, and justify your answer? So when is displacement equal to 0? So once again, it's that idea of when's the area above equal to the area below. And looking at our picture, that rectangle obviously has an area of 2, I know that. The area of that next section, I'll just call it A. But it looks like that's a pretty symmetric, it looks symmetric. So I'm going to assume that is also A. So now I want a rectangle that has an area of 2 there. Well, the height of that rectangle is also 2, so that width then must be 1. Putting that all together, I can work out, well, that's after 4 seconds. It turns out to be back there. Now we're going to draw the acceleration graph. So this time I've got a velocity. Instead of integrating, we're going to draw the derivative of that. Differentiate a horizontal line. Well, differentiate a constant, we get 0. We're going to get the axis. So we know we're just going to be on the axis between those points. From 1 to 3, look, I don't know the equation. Kind of looks like a cubic to me. I'm going to assume it is. I know it inflects at 2. It's also decreasing. So I'm going to get a parabola. It will be stationary at the same x value as the inflection point. It's decreasing, so I know it's negative, it's below the axis. So all right, I'll just draw some sort of a parabola there. 5 to 6, again I'm making some guesses, but it kind of looks like that arc is the same as the arc in what I just assumed was a cubic. So I should get the same sort of picture then. I assumed the other one's going to be a parabola, so I reckon this is going to be some sort of parabolic thing too. So there we go. Stationary at 6, it's going to be above because it's increasing, and I've got this weird graph for acceleration. Alright, that shall do it.